Okay, so for decades, one material has really been king when it comes to high explosives. RDX.
The workhorse, yeah.
Yeah.
Relatively easy to make, used in tons of applications.
Exactly. From artillery shells, demolition charges, you name it. But let's be honest, RDX has always had this major drawback.
It's touchy, very touchy.
Yeah, sensitive to impact, friction, heat. It's a genuine safety headache. So, all right, let's unpack this. For the last 25 years or so, researchers have been searching hard.
On a mission, really.
Yeah, looking for a successor, something with that RDX level power, but crucially, much, much less likely to, well, go off when you don't want it to.
And that whole search leads us straight to today's topic. This really interesting molecule, level 1 diamino-2 dinitroethene.
Or, thankfully, FOX7 for short.
Much easier.
Yeah.
FOX7. It seems kind of unassuming, but it's been under the microscope for ages as a potential and much safer RDX replacement.
Exactly. So for this deep dive, we've really gone through a pile of research. Our aim is to properly get to grips with FOX7. We'll look at its basic structure, how it's actually made, what happens when it gets hot,
Thermal behavior.
how scientists spot it, its spectroscopic fingerprints, and the big one, how its bang compares to RDX.
And we'll touch on some other related high-energy stuff, too, and how computers are playing a massive role in all this.
Definitely. So where do we start? The synthesis, how it was first made.
Yeah, that's fascinating, actually. The first successful synthesis was back in '98. A group at FOI in Sweden managed it.
Okay.
But the process involved nitrating 2-methylimidazole and then hydrolysis. It was tricky.
How so?
Well, the conditions had to be just right, and even then, the amount of FOX7 they actually got out.
Yeah.
It was pretty small, low yield.
So a breakthrough, yes, but not exactly ready for prime time.
Precisely. It showed it could be done, which was huge, but manufacturing it that way, not practical.
Right, you can just imagine trying to scale that up. Fiddly. But scientists don't give up easily, do they?
Thankfully not. They found a much better way. They started with something you can actually buy off the shelf. 4-volt-6 dihydroxy-2-methylpyrimidine.
Okay, a commercially available starting point. That sounds promising.
Exactly. And here's the clever bit. Nitrating this compound gives you an intermediate product that's actually a solid, and you can isolate it easily.
Oh, I see. So you can purify it before the next step.
Yes. That intermediate, it's got a bit of a mouthful of a name. 2-dinitromethylene 5-L5-vinitrodihydropyrimidine 4,6-1H-5H dione.
Wow. Okay.
But the point is, it's isolable. And that makes the final step, the hydrolysis, to get FOX7 much more controllable.
How much better did the yield get?
By tweaking the hydrolysis conditions, like how much acid is left, when you add the intermediate to water, they push the yield way up, over 90%.
90%, that's huge.
Massive difference. Suddenly, large-scale production of this safer alternative looked, actually feasible. So what this means for you listening is that making FOX7 efficiently became a real possibility.
Absolutely, a game changer for potential production.
Okay, so we can make it efficiently now. What does the molecule itself actually look like up close?
Well, fundamentally, the FOX7 molecule is pretty much flat, planar.
Okay.
The bond lengths, the carbon double bond, the carbon nitro bonds, the carbon amino bonds, they're all quite specific. But what's really key are these strong hydrogen bonds within the molecule.
Intramolecular hydrogen bonds.
Exactly. Little attractions between the hydrogens on the amino groups and the oxygens on the nitro groups. They kind of hold the molecule together tightly.
And those internal bonds must affect how it behaves overall.
Hugely. They're critical for its stability and properties.
So how do these flat molecules pack together when they form a solid crystal?
Right. So in its usual form, the alpha polymorph, you get 4 FOX7 molecules in each basic repeating unit of the crystal. Specific dimensions, of course. But the really cool part is the bigger picture. They arrange themselves into these wavy infinite layers.
It's like graphite. A bit like graphite. Yeah, or another insensitive explosive called TATB. Similar layered structure. Within each layer, those hydrogen bonds we mentioned are key, holding the molecules side by side.
And between the layers?
Between the layers, it's weaker forces holding them together, Van der Waals forces. The gap between layers is about 3 angstroms.
How does that compare?
It's tighter than graphite, which is about 3.5 angstroms, but much, much tighter than TATB, where the layers are further apart, around 6 angstroms.
Interesting. So with all those strong bonds holding things together, I guess it doesn't dissolve easily in just any old solvent.
You got it. That dense network of hydrogen bonding makes it tough for common solvents like acetone or acetic acid to pull the crystal apart.
So what does dissolve it?
It tends to prefer what we call polar aprotic solvents, things like DMF, NMP, DMSO. They interact with it differently.
Okay. And water.
Practically insoluble in water. Yeah.
Now, I think I read somewhere that FOX7 isn't always the same structure. Like, it can exist in different forms.
Yes, polymorphism. Good point.
Yeah.
Think carbon. You've got diamond and graphite, same element, different structures, different properties.
Right.
FOX7 does that too. You can arrange its molecules differently in the crystal. We call these different arrangements polymorphs.
And how many are known for FOX7?
So far, they've clearly identified at least 3. Alpha, beta, and gamma. They use techniques like X-ray diffraction, DSC, TG, thermal analysis, basically.
Any of these transitions particularly important?
Well, the switch from the alpha form to the beta form is quite interesting. It happens around 113 degrees C. It's reversible, absorbs heat.
Endothermic.
Yep, endothermic. And importantly, the material expands slightly when it goes from alpha to beta, about a 1.9% volume increase.
That could matter in munitions, couldn't it? Temperature changes during storage?
Exactly. That expansion and contraction could be a factor. Potential implications for long-term storage stability, absolutely.
And the other transitions, you mentioned gamma.
Yeah, there's another shift from beta to gamma around 173 degrees C. But that one doesn't seem to completely reverse when it cools back down. It's partially reversible.
Okay. And wasn't there some confusion about transitions at lower temperatures?
There was. Some older studies mentioned seeing things happen below 100 degrees C, but it's still a bit debated.
Why the uncertainty?
It seems like how the sample was made, if it was recrystallized, the particle size, things like that can really influence when these transitions happen and how fast. So the picture below 100 degrees is still, well, a bit fuzzy.
Okay, so a complex character structurally. What about when you really heat it up? Does it melt before it decomposes?
No, that's another difference from some explosives. FOX7 decomposes directly from the solid state. Doesn't melt first.
And when does that kick off?
It starts becoming significant above 200 degrees ASC. But just like the phase transitions, how it breaks down can look a bit different depending on the sample's history.
Even if the samples seem the same.
Yeah, you can run thermal analysis, DSC curves, and sometimes see one peak, sometimes 2, these bursts of energy release, usually somewhere between 235 and 275 degrees C.
But it's all done by when?
Generally, the decomposition is complete by about 300 degrees C.
And what's left? Or rather, what gases are given off during that breakdown?
It's quite a mix. You get carbon dioxide, CO2, hydrogen cyanide, HCN,
Nasty stuff.
nitrous oxide, N2O, nitrogen dioxide, NO2, isocyanic acid, HOCN, water, of course, and nitric oxide.
Any patterns in when those appear?
Interestingly, NO seems to come off in both the early and later stages, but things like nitrous acid and formic acid seem to be mainly in the second decomposition step.
Have they figured out the energy needed to start these steps? Activation energies?
They have. Calculated values for the 2 main decomposition steps are around 238 and 322 kilojoules per mole. Higher numbers mean it takes more energy to get it going.
Okay. And wasn't there an idea about different regions within the solid?
Yeah, there's a hypothesis that samples might contain both highly ordered crystalline bits and less ordered amorphous bits.
And that affects the decomposition.
The thinking is that heating or recrystallizing the FOX7 can change the ratio of these regions, and that affects the thermal behavior you observe. So its history matters.
A bit of a chemical chameleon, then. Fascinating. Okay, switching gears a bit. How do scientists actually know they're looking at FOX7 in the lab? What are its fingerprints?
Spectroscopy is key here. It has really distinct signatures. NMR, nuclear magnetic resonance, is very powerful.
What does that show?
It tells you about the environment of the different atoms. For instance, the proton NMR shows the hydrogen atoms on those amino groups are pretty similar. They give one broad signal.
Okay. And carbon?
Carbon-13 NMR shows 2 main signals, one for each type of carbon atom. The ones attached to the nitro groups are usually weaker signals, which tells you about the electron distribution.
And nitrogen NMR?
Nitrogen-15 NMR confirms you've got both the nitro group nitrogens and the amino group nitrogens, each showing up in their expected place. It all fits the structure.
Right. Are there other spectroscopic methods they use?
Oh, yes. Infrared spectroscopy, FTIR, is common. It looks at how the molecule vibrates. You see characteristic peaks for the NH2 wiggles and stretches, and for the NO2 groups too.
Like a vibrational fingerprint.
Exactly. And Raman spectroscopy gives another complementary vibrational fingerprint by looking at scattered light.
What about UV light?
Yep, ultraviolet visible or UVV spectroscopy. If you dissolve FOX7 in water and shine UV light through it, it absorbs strongly at 3 specific wavelengths. You get a characteristic spectrum there too.
So, plenty ways to identify it. All right, let's get to the really crucial bit, performance. How does it stack up against RDX as an explosive? We keep saying it's safer.
Yes, and it definitely is. Significantly less sensitive to impact than RDX, and remarkably insensitive to friction. That's a huge plus.
But what about the power, detonation velocity, pressure?
Okay, so raw figures.
Uh,
Its detonation velocity and pressure are actually slightly lower than RDX's.
Ah, so less powerful then.
Not so fast. This is where it gets interesting. At OX7 has a higher maximum density, meaning you can pack more of it into the same volume. About 3% more by weight compared to RDX.
Okay, so higher density compensates for slightly lower intrinsic energy.
It helps significantly, yes. That density advantage is really important. It means if you're comparing equal volumes, the performance gap narrows considerably.
How does the stored chemical energy compare? Enthalpy of formation.
That's another difference. FOX7 actually has a negative enthalpy of formation, meaning it's more stable than its constituent elements. RDX has a positive one, meaning it's less stable.
So FOX7 starts from a more stable place, but the release of energy upon detonation.
When you calculate the actual energy released during detonation, and you factor in that higher density, the energy density, the bang per unit volume for FOX7, gets surprisingly close to RDX.
How close?
Calculations vary a bit, but some suggest it might only be about 5% lower in terms of energy per cubic centimeter.
Wow, okay. That is close. So the takeaway is safer, yes, but performance-wise, volume for volume, it's pretty much right there with RDX.
That's a fair summary. It's not just safer. It's potentially a near drop-in replacement in terms of the force delivered from a given size charge.
That's impressive. What about the gas produced? That's important for the explosion effect too, isn't it?
It is, yeah. The amount of gas generated pushes things apart. Mole for mole, RDX actually produces more gas than FOX7.
Okay.
However, if you compare them based on mass, say, per kilogram of explosive EVO, the gas volumes are very similar.
And by volume of explosive, since FOX7 is denser.
Then FOX7 actually comes out slightly ahead. It produces a bit more gas per cubic centimeter than RDX does.
So looking at energy density and gas production per volume, FOX7 really hold its own.
Absolutely. It stacks up very well against the old standard.
Okay, we've covered its structure, how it behaves, its performance. But can you do other chemistry with it besides, blowing it up?
Yes, definitely. It's not just an explosive. It's a chemical compound that can react in interesting ways.
Like what?
One reaction type is called transamination. You can actually swap out its amino groups, the NH2s, for other amine groups.
So you can modify the molecule.
Yeah, depending on the amine you use, you can replace one or both amino groups. If you use something with two amino groups, a diamine, you can even make cyclic ring-like structures incorporating the FOX7 backbone.
Huh. Any other reactions?
It can also rearrange itself.
Yeah.
Isomerization reactions can turn it into different compounds, like ammonium cyanodinitromethanide or guanidinium dinitromethanide. Just shuffles its atoms around.
Sounds quite versatile. Are those amino groups generally very reactive? Easy to modify?
Actually, they're less reactive than you might think. For some reactions, like getting them to react with 1-urdol-2-dibromoethane, you need to sort of activate them first.
Ow.
Often using a strong base, like sodium hydride, it makes the nitrogen atoms more keen to react.
But not always.
No, other reagents like oxyl chloride react quite readily without needing that activation step. So it depends on what you're reacting it with.
Were there other ways people tried to make FOX7?
There were attempts, yeah. People tried nitrating triazine rings, hoping to get FOX7 or related structures, but those routes generally didn't work out. They tended to form other things, like cyanuric acid.
Right. Now the name FOX7, it implies maybe there are FOX1 through 6? Or maybe other isomers, different arrangements of the same atoms.
Good question. FOX7 specifically refers to the trans isomer of diamine and nitroethene. The atoms are on opposite sides of that central double bond.
Is there a cis isomer where they're on the same side?
Yes, the cis isomer exists too, and scientists have done theoretical calculations to compare them.
Which is more stable?
In the gas phase, the calculations predict FOX7, the trans isomer, has lower energy, so more stable. And that holds true for the solid state too. FOX7 is the most stable solid form found so far.
But what about energy release? If the cis isomer is less stable, does it release more energy when it detonates?
That's the interesting prediction. While FOX7 is the stable one to have, calculations suggest the cis isomer might release slightly more energy per gram upon detonation, potentially even closer to RDX on a weight-for-weight basis.
So why the big focus on FOX7, the trans one, if cis might be slightly punchier per gram?
It likely comes down to stability and practicality. FOX7 benefits from those strong internal hydrogen bonds we talked about earlier, And also a better push-pull electronic effect.
Push-pull.
Yeah, the electron donating amino groups pushing electrons and the electron withdrawing nitro groups pulling them. This electronic communication across the molecule adds to its stability, makes it easier and safer to handle.
And the theoretical models generally back up what we see experimentally for FOX7.
By and large, yes. The calculated structure, properties, they match well. Although, interestingly, the models haven't quite managed to simulate that alpha to beta phase transition perfectly yet. Still some nuances there.
Right. You mentioned earlier we'd touch on other high-energy materials being researched. What else is out there beyond FOX7?
Oh, it's a really active field. A huge variety of chemical structures are being explored.
Such as?
Well, there are other cyclic nitramines related to RDX, but
Okay.
maybe with different ring sizes or more nitro groups, aiming for higher energy.
Okay.
Then you have things like nitrocubanes, heptanitrocubane, octanitrocubane. These cage-like molecules with incredibly high densities. Very powerful, theoretically.
Hard to make, I bet.
Extremely challenging, yes. Then there's a lot of work on nitrogen-rich salts. Based on heterocyclic rings like tetrazoles and triazoles, these often have high heats of formation, lots of stored energy, and good densities.
More nitrogen usually means more energy release, right?
Generally, yes, and more gas production.
Yeah.
There are also organic difluoramine derivatives compounds like HNFX, TNFX using fluorine to boost performance.
So lots of different chemical families being explored.
Absolutely. And beyond specific molecules, there's even really fundamental research looking at pure nitrogen under extreme pressure. Could it form stable, high-energy phases?
Wow, solid nitrogen as an explosive.
Potentially. Way down the line. It's very theoretical right now. But for all these synthesized compounds, researchers are carefully measuring detonation velocity, pressure, sensitivity, building up the data.
Sounds like making some of these must be pretty hairy in the early stages.
You could say that, like trying to bake a very, very temperamental cake, perhaps. One tiny mistake.
Right. And you also stressed how important computers are becoming in this field.
Indispensable, really.
Yeah.
Computational chemistry is huge for HEDM, high-energy density materials.
What can they predict?
Things like crystal density, which is crucial for performance. How much energy is stored, the heat of formation, even getting towards predicting sensitivity, though that's still very complex.
How do they predict density, for example?
They use methods that look at the molecule's calculated volume, its electrostatic potential, how charge is distributed, and use that to estimate how tightly the molecules will pack together.
And heats of formation.
Yeah.
Energy content.
There are various computational approaches using quantum mechanics to calculate that for the gas phase and the solid state. It can get tricky, especially for compounds with lots and lots of nitrogen atoms.
And you mentioned computers modeling that high-pressure nitrogen stuff, too.
Exactly. Doing experiments on a computer that would be incredibly difficult or impossible in a lab, predicting potential new structures and their stability under extreme conditions.
Okay, finally, let's just circle back to sensitivity. It keeps coming up as maybe the most critical factor for a practical explosive. Why is it so hard to predict why some things are touchier than others?
It's just incredibly complex.
Yeah.
Sensitivity isn't down to one single molecular property. It's a mix of things.
Like what?
Crystal defects play a role. Imperfections in the solid structure can be initiation points. Then there's the actual chemistry of the very first reaction that happens when it's hit or heated the initiation reactivity. And the overall molecular structure itself, of course.
How do they test it experimentally?
Standardized tests, Druckhammer tests for impact sensitivity, friction tests where materials are rubbed together, wedge tests to see how it reacts to a shock wave.
Trying to get objective measures.
Right, and theoretically, people are trying hard to find correlations. Can we link sensitivity to electronic structure, to NMR signals, to that electrostatic potential we mentioned?
Any breakthroughs there?
Progress is being made, but honestly, it's still a really challenging area. A complete predictive understanding of sensitivity across all materials. We're not quite there yet. It's still a major focus of research.
Okay, so pulling this all together, FOX7. It really does seem like a very strong contender, doesn't it? In this whole search for something safer than RDX, but still potent.
Absolutely. I think our deep dives shows that pretty clearly. The safety profile is a significantly better, less sensitive to impact, much less sensitive to friction. That's a huge win.
And the performance.
When you account for its higher density, the performance is remarkably competitive. Energy density, gas volume per unit volume, it's right up there, maybe even slightly better in some ways. Research is ongoing, but it's clearly very significant.
And it highlights this whole dynamic field, doesn't it? The broader search for new HEDMs. It's this constant interplay between lab work and computer modeling.
Exactly. Meticulous experiments combined with increasingly powerful computational tools, all trying to push the boundaries of chemistry and physics.
It really is a balancing act, isn't it? Performance versus safety.
That's the core challenge. Maximize the energy, minimize the risk, and fundamental understanding, both experimentally and computationally, is what drives progress.
So a final thought for you, listening. We've talked a lot about these trade-offs, safety versus power, density versus intrinsic energy. Thinking about developing the next generation of these materials, what do you think are the most critical factors? What should guide that development? Something to mull over.
Definitely. We'd encourage you to look deeper into the research we've discussed, or just explore the fascinating world of high-energy density materials further. There's a lot out there.